You hear that word all the time, right? Algorithm. It's in your social media feed. It's deciding what movies you see. But what does it actually mean? Well, today, we're going to pull back the curtain on this huge concept and see why it's one of the most fundamental building blocks of our modern world. So when you hear algorithm, your brain probably jumps straight to complex lines of code, right? Some super high-tech computer stuff. But what if I told you that you've been using algorithms your entire life, probably even this morning, and you didn't even know it? Yep, that's right. An algorithm, at its core, is just a step-by-step process. Something you do the same way every time to get the same result. Tying your shoes? That's totally an algorithm. That loop, swoop, and pull thing is a set of steps you can repeat. Following a recipe to bake a cake? That's a classic algorithm. Even your bedtime routine, brushing your teeth, changing clothes, setting an alarm, that's a personal algorithm you run every single night. Okay, so if an algorithm can be as simple as making a cake, how does that same exact idea scale up to run pretty much our entire digital world? Well, the jump from one to the other is actually surprisingly simple. Here's the textbook definition, and the keywords you gotta focus on are clear, precise, and finite. Each step has to be totally unambiguous, no room for confusion, and this is super important, an algorithm has to end. It's got a job to do, and it has to have a finish line. This slide right here really makes it all click. Just look at the structure. A recipe has inputs, your ingredients. It has a processing stage, you mix, bake, and cool, and it has an output, a cake. A computer algorithm follows the exact same pattern. It takes in data as its input, it processes that data using a bunch of logical rules, and it spits out a result or a decision as the output. See? The underlying logic is identical. But this is where things get really, really interesting. Because just having an algorithm that works, well, that's not good enough. In computer science, the goal isn't just to solve the problem, it's to solve it in the most efficient way possible. Think about a simple problem we all know how to do, multiplication. We learned a method back in grade school that works perfectly, every single time. You line up the numbers, you multiply, you shift over, you add it all up. It's a totally reliable algorithm. But here's the question a computer scientist always asks. Is it the fastest way? Is it the most efficient way to get the job done? Especially when the numbers aren't just 41, but are thousands or even millions of digits long. And as this quote from Carnegie Mellon's School of Computer Science points out, the first, most obvious way you think of to solve something is almost never the best way. There's pretty much always a smarter, faster path if you look for it. Now, take a look at this. You don't need to be a math genius to get the big idea here. That running time column basically tells us how fast the algorithm is. The smaller that little number up top is, the faster the algorithm. So back in 1962, a mathematician named Karasuba discovered a way to multiply that is way more efficient than what we all learned in school. This was a massive breakthrough, and it all came from just rethinking the basic steps. So the goal is always the most efficient algorithm, right? Well, not always. Sometimes finding the absolute perfect answer would take a computer years, literally. And in the real world, we usually need an answer now. This is where something called a heuristic comes in. It's all about this trade-off between a perfect answer and a good enough answer that we can get super quickly. This table really breaks down the difference. An algorithm guarantees you the best possible result every single time. A heuristic is more like an educated guess, a mental shortcut. The perfect example is your GPS. It could spend hours calculating every single possible route to find the absolute fastest one, down to the millisecond. But by then, you'd be super late. Instead, it uses heuristics to find a really good route in just a couple of seconds. It trades perfection for speed, which is exactly what you need. Okay, so this brings us to a super practical question, especially if you're learning to code. If we have all these amazing pre-built tools, why do we even need to understand the theory behind them? You see this question on forums like Reddit all the time. And you know what? It's a fair question. If your programming language lets you just type .sort and it magically sorts everything, why would you bother learning all the complicated theories behind how sorting actually works? And this analogy just puts it perfectly. A doctor prescribes insulin, that's the tool, but they can only use that tool effectively because they have a fundamental understanding of the biology, of how the pancreas works. If they didn't have that deeper knowledge, they'd just be treating a symptom without ever understanding the cause. It's the exact same thing with coding. Here's another way to think about it. You don't need to know how an engine works to drive a car, but if you want to build a race car, you absolutely do. So the question becomes, do you want to be a driver or do you want to be a builder? And really, that's what this all boils down to. Knowing these fundamentals is what allows you to go beyond just using the tools other people have made. It gives you the power to analyze, to optimize, and to build the next generation of tools yourself. It's the foundation for real problem solving and innovation. So we've seen that algorithms are truly the building blocks of our digital world. But as they get more and more powerful, as they shape more of our lives, the really big question becomes, who gets to be a builder? Who has the knowledge to create and not just consume? That's the challenge for all of us. Thanks for joining me for this explainer.